All right, so this lecture will be a full-length lecture rather than split into several mini modules. It's just easier and more coherent that way. And it will provide a general overview of the tectonics of Western North America, sort of stepping consecutively through geologic time from the late Precambrian to the present day. And the way in which it's organized makes use of this beautiful book by Ron Blakey and Wayne Ramey, in which they've used the published geologic literature to reconstruct the paleogeographic features of, in this case, Western North America, although they have these types of reconstructions for other orogenic regions as well. And their paleogeographic maps include a lot of nice detail as shown on the right-hand image, including topography that might be associated with different types of plate boundaries, for example, trenches versus mountain belts, different types of oceanic and continental basins, etc. So I'll be using a lot of these paleogeographic maps to illustrate the tectonic evolution throughout this lecture. I'll also be showing commonly on the left side of slides the geologic timescale and the eon areas, periods, etc., or eras, periods, etc., that the map represents. All right, so any discussion of North American tectonics has to first start with distinguishing its cratonic core, referred to as Laurentia, from everything else that's been accreted to it since the Precambrian. And just to remind all of you what a craton is and where they're exposed globally, cratons are thick sections of continents that have remained stable and mostly undeformed since the Precambrian. They include both Archean sections, those are older than 2.5 billion years old, and Proterozoic sections, referred to as shields, but those are also considered what's traditionally cratonic. The Archean cratons are gray in this image, and the shields are orange. Everything else shown in green is related to Phanerozoic orogenic events and could be thought of as more sort of mobile compared to the rigid cratonic cores. In cross-section, cratons are thought to form these continental keels where the crust and lithosphere is substantially thicker than the Phanerozoic continental material. If we look at global S-wave velocities, for example, this is an image taken at 250 kilometers depth, and you can pick out several of the cratonic sections just based on their faster S-wave velocities at 250 kilometers, indicating there's still relatively dense, cold lithosphere at these depths beneath the cratons. So North America's cratonic seed, so to speak, is called Laurentia, and it consists of both Archean and Paleoproterozoic components. The Paleoproterozoic section consists of these subparallel tectonic belts that represent very old subduction or collisional orogenies. Through the Phanerozoic, most of this cratonic core has remained undeformed, but parts of it have been entrained in subsequent deformational events or remobilized, including the region shown in pink on the map here on the right, which includes, for example, part of the Colorado Plateau, which we'll talk about later. The best exposures of the cratonic rocks are in places, or that is, places where it isn't covered with later sedimentary rocks, for example, are in the Canadian Shield, all of the reddish colors on this map. A few exposures of the cratonic material show up along the margins of the Colorado Plateau, also in the Rocky Mountains, but otherwise the Canadian Shield is the main place to study these rock types. Here's what a typical landscape and geologic exposure of the Canadian Shield looks like. It's referred to as a shield because of how subdued and broad the topography is. The rock types here are dominantly nondescript orthogneisses with evidence for many phases of deformation, melting, and intrusion. The example on the left is a nice sheath fold in gneiss that's then cut across by an igneous dike. The image on the right, a typical Augen gneiss, strongly foliated with nice feldspar porphyroclasts forming the Augen there. The original shape of Laurentia and many of the other continental cratonic seeds was determined by the breakup or rifting of the Neoproterozoic supercontinent known as Rodinia. And this rifting ultimately led to the formation of large ocean basins, particularly on the west side of Laurentia. And this means that for a significant portion of geologic time, the western margin of Laurentia was actually a passive continental margin, similar to what the east coast of North America, the Atlantic side, is today. In cross-section, this would have looked like this image in the upper right with a subsiding continental margin and syn-rift sediments followed by shallow marine deposition of sandstones and marine carbonates. And this sequence of Proterozoic syn and post-rift sediments is preserved primarily in the Grand Canyon and is referred to as the Grand Canyon supergroup. The base of the Grand Canyon supergroup is mainly syn-rift sediments and volcanics, whereas the upper section is syn and post-rift dominantly sedimentary sequences. And so since the breakup of Rodinia, the cratonic seed of Laurentia has had sections progressively accreted to it on all sides, and this combination of cratonic core and orogenic mobile belts is what defines the current continent of North America. And if you think about modern day tectonic plate boundaries, especially convergent or accretionary ones, you can get a pretty good idea of what these accreted sections of the North American continent probably consist of. So for example, the modern day configuration of plates suggests that active convergent margins involve all sorts of different types of lithospheric collisions, from continental fragments to remnants of island arcs to scraping off of oceanic plateaus to subduction of volcanic hotspots or oceanic ridges. So all of these same features are ultimately what compose the accreted terrains that ultimately attach themselves to Laurentia to define the full North American continent. And we'll come back to some specific examples for the Western US Cordillera in a few minutes. But in the meantime, let's continue tracking the development of Laurentia through geologic time. So once we get to the Cambrian, a large sea level transgression is thought to have covered a significant part of the Laurentian craton with a shallow epicontinental sea. A sea level transgression, you may recall from historical geology courses, simply represents a global sea level rise, typically related to both tectonics and climatic effects. And there have been many transgressions and regressions that affected North America, as shown on the diagram on the right. The yellow areas represent regressions where sea level drops, and therefore those are typically the times where erosion is expected and where unconformities should be forming. The green regions show sea level gradually rising, which are generally periods of substantial deposition. Some of these correlate well with ice ages or marine isotope stages, shown as blue bars, and others correlate well with orogenic events, and some of them actually just seem to not correlate with either. So just stepping through time a little bit here, by the end of the Cambrian, during what's called the Sauk transgression, most of southern Laurentia is covered by water. This persists into the Ordovician. The central region of the continent that is not submerged remains above sea level, and it's referred to as the transcontinental arch. Note that on the east coast, in the meantime, there's a small orogeny during this early Paleozoic time period where some island arc terrains collide with eastern Laurentia. This is referred to as the Tectonic orogeny. There's some bits of this, a record of this recorded by deep-seated rocks exposed in the Appalachian Mountains. So, okay, during the Cambrian Ordovician, most of Laurentia is covered by a warm, shallow sea. So you might ask yourself, well, what kinds of rocks should we expect to be there, and what kind of contact will those rocks form with the Precambrian basement? And not surprisingly, the rocks from this time period are typically sandstones, reef carbonates, tidal marine sequences, some shallow marine shales, and also not surprisingly, this time scale is characterized by a massive continent scale unconformity. This is what's known in North America as the Great Unconformity, and it's just called that because it's recognized over much of the central continent. Returning here to the Grand Canyon stratigraphy, one of the many places where this Great Unconformity is well exposed. So now we can see the tilted Rodinian rift sequence, the Grand Canyon supergroup I mentioned earlier, and it's overlain across a sharp angular unconformity by the marine transgressive sequence consisting of sandstone, shale, and limestone. Those are shown in kind of the greenish blue color labeled Tapeats, Bright Angel, and Muav. This Cambrian sequence is well known for its preservation of the first appearance of complex life forms such as trilobites and echinoderms. Here's what the Great Unconformity looks like in the Grand Canyon. In this case, it's just showing this layer cake shallow marine stratigraphy sitting atop the basement gneisses labeled the Vishnu schist formation here. Here's the same unconformity, but several hundred kilometers away in Wyoming, but again showing this sort of moderately dipping gneissic basement rock overlain by very nicely bedded shallow marine sequences representing the submergence of the continent to form this epicontinental sea. In general, the rocks associated with this epicontinental sea represent the thickest and best studied Cambrian Ordovician deposits in the world. But it has the most extensive exposures preserved in northwestern Canada and several good exposures in the Colorado River and Grand Canyon region. Note that the Grand Canyon stratigraphy also preserves some of the subsequent sea level transgressions and regressions, also bounded by periods of deposition that are bounded by significant unconformities, although in this case there's no deformation going on during the sea level rise and fall, so these are not angular unconformities. So let's keep moving ahead in time now, continuing into the Middle Paleozoic, the Silurian, Devonian time periods. And this is the time of the Caledonian and Akkadian orogeny. This event represents a collision between Laurentia and a small continental fragment that will later merge to form Northern Europe, known as Baltica. And the event is called the Caledonian in Britain, Ireland, Scotland, and Scandinavia, but it's called the Akkadian orogeny in North America, just different nomenclatures for the same orogenic event. Note, however, that during this time, the West Coast does seem to see a bit of tectonic activity with the rather stealthy approach of a small island arc chain toward the west. I'll just note, too, that sedimentary rocks from the Silurian Devonian are best preserved in the east central USA. So by the late Devonian, that island arc chain collides with North America to produce some fairly cryptic Devonian Mississippian thrust faulting on the west coast. There's no magmatism generated that we know of, but there's pretty much just this one structural feature that seems to record the collision of this island arc chain, the antler orogeny, and that is the formation of a large-scale thrust fault that pushes deep marine sedimentary rocks over shallow marine sedimentary rocks, known as the Roberts Mountain allochthon. The allochthon refers to the displaced block, and the autochthon is the footwall that is thought to remain in place. And although this is a cryptic feature now, its size or length of exposure suggests that there was significant compressional deformation. Here's a map of the Alakthon. It's this fault that the white arrow is pointing to. And here it's labeled with these terms that are sometimes still used, perhaps useful to know, called eugeoclinal, meaning deep marine, and myogeoclinal, meaning shallow marine. These terms are kind of funny because they date back to a pre-plate tectonics era where oceans were just considered deep basins within the global scale continents. But in any case, the main point is there's this big thrust fault that brings deep marine sedimentary rocks from the northwest toward the southeast and sets them on top of much shallower marine equivalents that are similar in age. So moving on to the late Paleozoic, during this time, the western US is thought to have remained fairly passive, with the exception of perhaps some small fringing subduction zones and island arcs that are preserved in a few locations in the northwest North American continent. But meanwhile, the continent of Gondwana is approaching Laurentia from the southeast. Just stepping through some of these reconstructions here. And this merging of Gondwana and Laurentia ultimately forms a new and improved supercontinent, known, of course, as Pangea. Here's the full configuration of Pangea as viewed from the geological record. I'm sure you're all familiar with it generally. And this supercontinent assembly is referred to as Alleghenian or Appalachian orogeny in North America, and it corresponds to the Variscan-Hercynian orogeny in Europe. The only signature of this supercontinent event in Western North America, however, is the uplift of the ancestral Rocky Mountains in the Montana and Colorado regions. This, of course, will be later overprinted by the much younger Rocky Mountain front once the Western North American Cordillera becomes active. Just stepping through these reconstructions for the Alleghenian orogeny here. Ultimately, this eventually entrains lots of older sedimentary sequences and in some cases basement rock to form the Appalachian Mountains. And the structural grain and mountainous topography that's associated with this event is still more or less preserved on the east coast of North America, although it's much more diffuse than in active orogenic environments. Here's a nice satellite image of some of the folds in the Appalachians, which now, thanks mainly to erosion, have their deep orogenic roots exposed. Unfortunately, though, the exposure is not spectacular due to the large amount of vegetation and the climatic conditions of the eastern US. Okay, so finally, the Mesozoic. This is where the North American Cordillera, as we think of it today, is truly born. So if we come back to the Laurentian cratonic core, we see that up through the Permian, there's still very little accretion along western Laurentia. But note that there are these fringing island arcs and curved subduction zones that are sort of collecting along the west coast at the end of the Paleozoic. Stepping through into the Triassic. And in the Triassic, some of these fringing island arcs start to attach themselves to North America, and they form what are referred to as exotic terrains. And what we mean by that is that they're thought to be island and island arc subduction complexes that were developed somewhere in the middle of the ocean, far from the North American continent, and then subsequently gradually accreted to the continent after they'd already formed and perhaps gone extinct. So this period in the Triassic is generally characterized by arc continent collisions, and much of the northwest US and Canada consists of these north-south striking belts of late Paleozoic to Jurassic accreted terrains. It's not until the Triassic that true east-directed subduction directly beneath the North American continent begins in what will eventually become Southern California. This is also where the earliest Cordilleran arc magmatism is recorded. Here's a map of the age of plutonic bodies in California, and you can see that some of them are Triassic in age, shown in pink. This is an example of the Triassic Butte volcanics in the Death Valley region in eastern California. And by the Jurassic, this east-directed subduction in the southwest side of Laurentia continues, and that's ocean continent subduction. But to the north, there's still more of this ocean-ocean subduction and sort of island arc docking or arc continent collision occurring. And this again is reflected in the geology of California. Southern California preserves this very well-developed arc, of course, known as the Sierra Nevada, that's stitched across continental rocks with an outboard accretionary wedge, whereas Northern California, in what's known as the Klamath Mountains, preserved many island arc terrains that are assembled over the same time period, but that range in age from early Paleozoic to Jurassic, and there's no really large coherent magmatic arc like we see in the Sierra Nevada. So these along strike variations in the geology are quite telling regarding the tectonic history, and it's where these reconstructions that I'm showing come from. Meanwhile, let's not ignore the East Coast because it also records early rifting of Pangea during this time. Rifts propagate on both the northeast and southeast sections of the continent as Pangea starts to break up. The Jurassic, coming back to the West Coast, the Jurassic is also a time where the continental interior starts to build topographically due to more coherent and coalescing subduction zones that are collecting to the southwest. This part of the continent is cut off completely from the coast, and it becomes quite arid and develops essentially a sand sea. The sand sea is what produces the Jurassic Navajo sandstone. This is the largest Aeolian sandstone in Earth's rock record. This is the formation that defines many of the state of Utah's iconic arid land national parks. The Navajo sandstone is a spectacular sequence of cross-bedded sandstones, all wind-derived, all Aeolian in origin. This is a section from the Arches National Park in Utah, and this very famous section called the Wave in Zion National Park, also in Utah. So all of that is sort of precursory to what most think of classically as the Cordilleran orogeny, which really begins in the late Jurassic and continues into the early Tertiary. In the mid-Jurassic, Cordilleran ocean continent subduction becomes more through-going, and Sierra Nevadan magmatism becomes quite vigorous. The Sierra Nevada batholith is built right across this oceanic continental transition, and the way we know this is based on the geochemistry of plutons that define the batholith. In particular, strontium geochemistry measured in plutonic rocks that punch through this boundary is an indicator of the lithosphere that the plutons actually intruded through. And so workers have mapped what's called a strontium 706 line that separates the paleocontinental boundary with continental material to the east and oceanic material to the west. And this line crosses straight through the center of the Sierra Nevada batholith and continues up through the Roberts Mountain Alachthon and up into some of the exotic terrains in Canada. If we come back to this map of Southern California, you can see that the volumes of emplaced magma are increasing through time, with small amounts shown in pink during the Triassic, a bit more shown in blue for the Jurassic, and the most voluminous magmatism occurring in the Cretaceous in the greenish colors. So there's this sense that the arc is progressively ramping up as subduction becomes more and more well-developed along the Cordilleran margin. The Sierra Nevada, of course, is another well-known section of the western US with its spectacular scenery and national parks such as Yosemite National Park as shown here. Just a quick detour to remind us of the action on the East Coast. In the late Jurassic, as the Sierra Nevada is ramping up on the west, Pangea rifting continues and an incipient Atlantic Ocean starts to form. And so as I step through the west coast events and subsequent sides, you'll see this ocean basin grow larger and larger to eventually form the Atlantic and the east coast passive margin. So as the Sierra Nevada is developing, a fold and thrust belt also starts to develop in the continental interior to the east of the arc. And at some point, this fold and thrust belt becomes high enough that stream flow switches from west directed toward the ocean to east directed toward the continental interior. And this is determined partly from paleocurrent directions in sedimentary rocks from this time period, and relatedly from the provenance patterns of detrital zircon, also from sedimentary rocks deposited during this time period. Note that even into the Cretaceous, though, some ocean-ocean subduction and island arc accretion still persists in the north of the continent, northwest side of the continent. In the Cretaceous, though, the topography in the foreland fold and thrust belt really starts to rise, and it coalesces into what would be characterized as a plateau that's sort of marching progressively eastward. And the load of this hinterland plateau creates a flexural foreland basin in the continental interior. And this leads to the development of a very expansive late Cretaceous, shallow, warm interior seaway that spans most of the central continent. The rocks associated with this seaway are primarily limestones, and these limestones and other shallow marine deposits commonly host very spectacular dinosaur fossils and trace fossils associated with Cretaceous organisms. Finally, by the late Cretaceous, the subduction zones appear to have coalesced at last into a single continuous oceanic continental subduction zone that spans the entire western Laurentian margin. In cross-section, this is what that classic Cordilleran margin would have looked like at this time, with the Franciscan accretionary prism to the west, the Sierra Nevada magmatic arc, the Sevier hinterland, this migrating eastward Sevier thrust belt, and then finally the stable Laurentian margin or the plate interior. If we zoom in a little bit on the forearc region, this is what people envisioned for the Franciscan accretionary wedge and the Great Valley forearc basin. This is what people envisioned this might have looked like in detail to the west of the Sierra Nevada arc. And here's those sequences as they are in map view. In the present day, they're of course shuffled substantially by overprinting San Andreas related right lateral slip, but otherwise they still preserve the general sequence of Franciscan accretionary wedge as the most outboard, the Great Valley forearc basin to the east of that, and then the Sierra Nevada arc to the east of that. There are some distinctive aspects of the Sevier fold and thrust belt that are worth mentioning because of how they'll contrast in a moment with a switch in Cordilleran tectonic style associated with the Laramide orogeny. But the Sevier thrust belt is well known for its thin-skinned thrust faulting, meaning that all of the thrusts develop in the sedimentary cover sequences, and they form along weak stratigraphic horizons or décollements. This is a cross-section through one of those thin-skinned fold and thrust belts in western Wyoming. You can see that most of the thrusts are developed along particular stratigraphic interfaces, and there's no basement-involved uplifts. Some nice field photos of the deformation style associated with severe thrusting, very kink-like folding and discrete faulting patterns involving only sedimentary rocks and not their underlying basement rocks. So this is going to contrast sharply with the next development in the Cordilleran sequence of events, which occurs in the early Tertiary with the onset of the Laramide orogeny. So if we look back at the late Cretaceous, we have this fairly uniform east-directed subduction boundary that's now developed along the North American margin. Here's the Sevier fold and thrust belt and its hinterland plateau. But as we move into the Paleocene and Eocene, some very distinctive structures start to be activated much farther into the continental interior in what is now the Rocky Mountain region. And this event leads to the development of the Colorado Plateau. That's a sort of this round, high elevation region surrounded by mountain belts on all sides. And this event is also associated with a fairly abrupt cessation of Sierra Nevada magmatism. So it basically shuts off the supply of volcanism to the magmatic arc. And so just looking at these tectonic provinces in map view, you can see where they are related to Western US state lines. The Sevier fold and thrust belt only extended into central Utah, whereas the Laramide structures jump several hundred kilometers eastward and raise the Colorado Plateau and define a zone of uplift much further inboard in New Mexico, Colorado, and Wyoming. This continental interior deformation associated with the Laramide continues into the Eocene, and the deformation patterns associated with it are really quite different in detail from the Sevier fold and thrust belt. Instead of thin-skinned thrusting only involving sedimentary sequences like shown on the left, the Laramide deformation patterns are referred to as thick-skinned because they characteristically involve the uplift of basement rocks forming these broad basement chord anticlines or monoclines with sediments on their flanks, but they do not show slip along the sediment-sediment interfaces or sediment basement rock contacts, in contrast to the severe thin-skinned deformation style. Here's an example. Here's an example of one of these monoclines with basement rock uplifted in the core and tilted sediments enveloping them on their margins. And these Laramide-based basement chord uplifts are substantial enough that they're what actually raises Precambrian basement rocks from the Proterozoic craton to the surface, whereas everywhere else these are buried by later sediment and later deformational events. And the Laramide event has perplexed geologists for several decades, but there's a general consensus that it probably relates to a period of flat slab or shallow angle subduction, much like the modern day Nazca Plate in the Peruvian Andes. What caused the slab to shallow is probably the most perplexing part, however, and no one really agrees on this, but some have suggested that it may have been due to subduction of an oceanic plateau entering the trench referred to as the Shatsky rise conjugate in this diagram. Okay, so now we'll move on into what should be somewhat familiar territory based on the earlier lectures on core complexes. The next phase in Cordilleran development involves basin and range extensional collapse. And the earliest extension appears to have begun in the Eocene in northern Nevada and Idaho. In general, the extension was concentrated in regions that were previously defined as part of the Sevier hinterland or the large thickened orogenic plateau. Extension starts to occur in the southwest, starting in the Alleghenian. But note that as the Laramide thrust faulting did, the extension occurs around the Colorado Plateau, but not really within it, suggesting that the Colorado Plateau is some sort of fairly rigid, undeformable block throughout Cordilleran history. Extension is most vigorous in the Miocene, such that by the Pliocene, most of the basin and range type topography has developed and the former severe hinterland plateau is pretty much entirely deflated or collapsed, so to speak. As we discussed in an earlier lecture, this basin and range extension produces both high-angle normal faults that define the basin and range topography, but it also produces these low-angle normal faults that bound metamorphic core complexes where the middle crust is exhumed. On the right-hand diagram, these metamorphic core complexes are shown as black blobs, and again, they're pretty much centered over the former severe hinterland, suggesting that the most vigorous extension correlates with what was probably the most thickened continental crustal regions. There's not much extension recorded in the Laramide contractional province farther to the east. So most of the extension is in sort of Idaho, Nevada, um, Arizona, and Eastern California. Just a map view now of the present day configuration showing the geology, and you can see that many of the basin and ranges dissect the orogeny along a wide corridor from north to south, and this repeats several of the early sedimentary packages that were deposited in the Paleozoic, while the west coast was mostly a passive margin. Some of the southernmost extensional areas also exhume some of the sort of late Proterozoic nice terrains as well, the rocks shown in sort of orange and red colors, basement type rock types. So finally, superimposed on top of ongoing basin range extension is the last and modern stage of Cordilleran development, which involves ridge subduction and the inception of the San Andreas transform fault, also somewhat familiar territory based on earlier lectures, most likely. So if we return to the Eocene reconstruction, you can see that off the coast of North America, the last vestiges of the Farallon plate, bounded by a ridge to the west, is approaching the subduction zone. And as the ridge that bounds the Farallon plate approaches the subduction zone, it eventually reaches the trench in the Oligocene. It subducts first in the south, just based on the geometry. And the subduction of that ridge starts to convert the Laurentian margin into a ridge-ridge transform fault. It sort of starts to unzip the San Andreas fault. In the Miocene, continued spreading along this ridge leads to incipient opening of the Gulf of California. And by the Pliocene, the San Andreas fault is really well developed and has already accommodated significant right lateral displacement along several strands, linking rifting in the Baja California region to rifting near the Mendocino Triple Junction. To the north, in what is now known as Cascadia, there's subduction of this last tiny remnant of the Farallon slab. It's now referred to as the Juan de Fuca plate, and that's active subduction occurring beneath Washington and British Columbia presently. Just as a final overview of that, this is a great animated reconstruction from Tanya Atwater showing this development in cartoon format. So you can see those last vestiges of the Farallon plate subducting. Ridge intersects, the ridge intersects the continent or the subduction zone at around 25 MA. Here you start to develop rifting in the Baja California region and sort of the unzipping and northward migration of the Pacific plate to form the San Andreas, and to the present day configuration with a small remnant of Farallon slab, the Juan de Fuca plate still subducting in the north. So that's a very broad brush overview of Western North American tectonics. It's based on an extensive amount of literature that was used to create those tectonic reconstructions that Ron Blakey did. And if there's some aspect of it that caught your attention that you're interested in learning more about, let me know and I can dig up some relevant papers for you. Here's just a summary slide of the sequence of events. And I'll see you all in class, and I'd be happy to take questions then or discuss some of these components of North American tectonics in more detail. Thanks for your attention.